In this example, we will antidifferentiate x to the fifth multiplied by e raised to the minus x cubed power. Now, my first observation looking at the integrand is no obvious algebraic simplifications, but there is maybe a obvious substitution that's worth attempting looking at that inside function minus x cubed. So let's go ahead and just let w be equal to x cubed. Then dw is 3x squared dx. So in order to rewrite our integrand solely in terms of this variable w, we somehow need to separate out the x squared to play the role of the dw. So we can write x to the fifth as being x cubed multiplied by x squared. And now that we've done so, we note that we have this extra x cubed left over, but that's exactly what w is equal to. So this is ideal. So 1/3 dw is x squared dx. So performing this substitution leaves us with a 1/3 dw, so that 1/3 pulls out front, and then w e to the minus w. And looking at the form of our integrand, this is something that is very well suited for integration by parts. And in terms of applying integration by parts, as we've seen with functions of the form of polynomial times an exponential, we'll want to let u be w and dv be e to the minus w. So v is minus e to the minus w, and du is simply dw. So we apply integration by parts. We're going to have the 1/3 hanging around out front, and it's multiplied by uv, so minus 1/3 w e to the minus w, and we're going to subtract away 1/3 of the integral v du. So a minus sign pulls out front to make it a plus. We have a 1/3, which is coming from in front of our antiderivative, and we'll be integrating e to the minus w dw. So a very reasonable integral has resulted here. Minus 1/3 w e to the minus w carries down, minus 1/3 e to the minus w plus c. And now that we've evaluated the integral that resulted after the substitution, we do need to resubstitute. So each of the w's that we see in our solution need to be replaced with that quantity x cubed. So minus 1/3 x cubed e to the minus x cubed minus 1/3 e to the minus x cubed plus c.